Once again to Nepal Engineering College. I am Arun Satyal. I am assistant professor here at Nepal Engineering College. I am the design and fabrication team lead for this Gulper iteration, our iteration of Gulper project. So, to talk about Gulper project, we have to go when it started for us. It started with our dear Professor Savitri ma'am. She said that if we can design and fabricate a machine that would help us pump safety tank from, let's say, from tank to a pit. Let's just transfer it. Can we do it? And we thought for a while and then came up with a pretty simple idea. We thought that we'd use a Venturi pump and just use electricity and pump it out. But then it all came back and haunted us, our idea, because we could not use electricity. It had to be a human operated machine. So here we are talking about a project in which we can make a pump for a society that is underprivileged, as I might say, who cannot afford to pay for the higher pumps. So while designing this pump, what philosophy that we adapted is, we thought of making pump from a junkyard. Junkyard everybody has. Everybody has this tire, everybody has this metal, everything. So while designing this project, what we thought was, we should use only parts that are available in the junkyard. So that it doesn't have to be in Nepal, it doesn't have to be in Ghana. If they know how it works, they can build them for themselves. There isn't any highly specialized parts or anything. So this came through. And before I talk about this, I want to talk about this. This is actually our V0. This told us that we can work. So we thought of designing a diaphragm pump. This is a diaphragm pump. What a diaphragm pump means, it's similar to our diaphragm. It takes in, stores it, and then throws out. It takes in, stores it, and then throws out. That's what we try to achieve with this. And here we are using this tire. It's from automobile, and this is a second-hand tire. We don't need a brand new tire. We need a tire that do not have any puncture holes in it. So what we did was, we set this tire. This was our diaphragm, and there are two holes. Obviously, here we need to close it. So we use the rim of the same tire as a negative that would fit directly into the tire. And trust me, it sounds easy, but it's not. Two rims took us 2 days to fit, just to fit, because it's so tight. It's a tight fitting. That's why they work, because air pressure will press this rim from behind, this rubber from behind into the rim, and there won't be air leak. That's for the vehicle. But first, there will be water inside. We need to make it waterproof. So what we decided was, we'd use the same rim that the tire goes into, and we purchased it and then covered this hole. Fortunately, there was no leak from this side while testing. And now coming to we have 3 ports here. This one is for priming the pump. Whenever you run a pump, you need to prime a pump. That's it. That is necessary. You cannot do anything about it. So this inlet is for priming. One is for outlet and one is for inlet. 2 inlets and outlets. Unfortunately, we were not able to complete this because of one very fundamental problem. Actually, it's a problem for us, because what we used was, as you can see, we have used cables to run this pump. These are cables, and cables work only when they are very under tension, very high tension. If to pump the water in, if we need, let's say, F amount of force, then the tension in the cable should be greater than that F. Otherwise, it will not work. What it will do is, if we apply any force to the cable, it will take that force and elongate itself if it is not pre-stressed properly. So this is the cable we use. And how does this work? It's simple reciprocating motion outside and inside. These two, you can see the plates. These are our moving element. If I just have to yank it to run the pump. So when it is coming outside, it is sucking in the material from the pit, and then when it is going inside, it is discharging the waste. So simply, it's a diaphragm pump that we have designed. Unfortunately, we cannot make it a working model because we have various problems, such as this. This in all three inlets have minor leakage. That is minor. We can do this. We can do that. We can control it. But the problem we had was we used the cable. We couldn't stress the cable enough to get the power that we have input here to get to the plate, because the power, the force that we apply, that way to elongating the cables. I don't think you get it. So what happens is, when I pull this cable this side gets stretched and it pulls the cable and it pulls it out. But if this cable is not stretched, let's say it's slack, however I pull, it won't pull this plate out. So the force that is required to pull this plate out, if this cable is not stretched beyond that force, it won't work. And we tried stressing it. We have two tensioners here. These are simple tensioners. This will just get this pulley one linear displacement. This tensioner will give linear displacement to this pulley. So we tried tensioning the rope, but what happened was our structure failed. Under immense stress, our support beam, it buckled. We couldn't stress beyond that. So because of that, we know the mechanism works, we know it sucks, and people have often said this is very big size pump you have developed. Here what we were hoping to achieve was, we were planning to displace this pump just by 1/10 of an inch. If this is displaced by 1/10 of an inch, then from the 3-inch hose, it will lift up, water will lift up around 4-5 inches. So that is a good displacement for a hand pump. That is equivalent to almost between 1 and 2 liters of water per stroke. That is a good thing, because we are not using any electricity or any other form of power, just a human operated machine. However, we are not able to do that, because now it is very easy. You can see I can just yank this input lever here and it will reciprocate. But when it is loaded with water, the force required is too high and the cable slips about the pulley. The force that we have applied to the system, it does not get transmitted to our diaphragm. That keeps on changing its shape, and that's how we get the power. So we have demonstrated here that this is a reasonable model for further investigation, but unfortunately we are not able to complete this at this iteration, let's say. But however, we are very proud. All our team, 3 of us designed and worked in this project, including and Savitri ma'am. 3 of us and Savitri ma'am. 4 of us, we took on this project. We tried it, we gave our best, but we couldn't make it work. But anyhow, I am thankful that I could show you a physical item here with a mechanism here among all of you today here. Thank you. Any questions?
Do you have diaphragm like that inside that?
This is the diaphragm. This tire itself is the diaphragm.
Okay.
It is shrinking and it is expanding. It is shrinking and it is expanding. So volume inside the tire, it's going down and going up, going down and going up. The volume change inside this tire because of this reciprocating plates will provide the pumping action.
Do you think it will lift? It can lift?
There are challenges for us, like here we use 3-inch pipe hose. The amount of water, that volume there was in the pipe, it was difficult for us to lift. Maybe that was also the problem, that we couldn't stress this. If we would have used if we would have used a small diameter inlet and outlet, maybe we might have overcome the force that was required to pull this plate out. But we have to do and see to know for sure how to go. Yes, ma'am.
Thank you, and so nice you used the waste.
Yes.
So very appreciative of you. But I was wondering, when you briefly you said water, but the thing we want, the slurry will have different properties than water. It will also have solids, and the water will be thicker. Will the same theory apply for it too?
Yes. The thing is, now we are talking about a very viscous solid, viscous liquid. It's not liquid, it's not plain liquid, but viscous liquid. Even for viscous liquid, what we use is pump. Right? We use pump to transfer liquid from one place to another. So this is also a pump. Given enough mechanical advantage to the system, I believe we can do that. That's why we started with this. So for the solution, we can make the system smaller and more practical, but it would be very hard to machine, because to develop this pump, we need at least one hole from where we can fit our hands, because we need to bolt all these in place. If we don't give any leverage behind, then we cannot. That's why we decided to use a 3-inch hole in the beginning, because to manufacture this, you need at least somebody's hand going inside it when it is closed from all end. I have to answer.
What's the next stage, bro?
Sorry?
The next stage.
Next stage. Okay, for this, my thinking is, our main problem is the force that we could not transmit to this diaphragm. So let's reduce the force at first. How can we do that? We can reduce the dead volume of our water. We used, let me show you, we used this as a suction. This was our suction hose. It's too big for this because it carries a lot of dead water, dead volume within it. So it was hard to lift for us. So for next iteration, what we are thinking is we will work on the same pump, but we will reduce the size of this pipe, so the weight of the water that we have to suck up, it reduces, and the force that we apply to the diaphragm, it will be able to pull the weight of the water that is within the, because ultimately it's the weight in this pipe that it has to pull up to discard it. So yeah.
I think it requires at least 1 horsepower force to lift, yes?
Yes.
Because of the size of the pipe and other thing, yeah?
No. Yeah, we need 1 horsepower force, but what we are trying to do is we are trying to multiply the force using mechanical advantage. Because, see, our driver here is simply, I can use it like this as well. I have to give it a lot of force, but if I do like this, it's more easy, right? But I am transmitting the same force. If I get it maybe 5 feet long, stay 5 feet away and just do this. Now you can provide enough force because of the leverage, and we don't want a huge amount of displacement. We talk about 1 inch, right? For every inch of this plate displacement, there will be around 35 liters of water. So we don't need to pump 35 liters of water at a time. Just thinking about doing it about 1 to 2 liters every stroke. So we didn't set, although we made this pump this big, we didn't set a very high goal. We just wanted this plate to displace at least 1/10 of an inch. 1/10 of an inch of this plate's displacement will do the job. So I think, we need horsepower, we need power. Nothing can be done without it. But even so, we didn't aim to displace this by 1 inch, which is almost about me yanking it from here to here. I don't need to do that. I just can sit in this place with a long bar and just this much. It will cover a small angle, small displacement. Nonetheless, because of the area of our diaphragm, that small displacement will translate into a larger volume.
Thanks, I think it's brilliant. I really like the idea and I can see it working. Do you think there's an alternative to using the cables in terms of whether cogs could be used from a gearbox, from an old car?
No, not gearbox. We need something that would reciprocate. Both. The reason behind using this again comes back to our junkyard philosophy. Because we thought of a system. What is the system that is less complicated? As less complicated as possible. We, being mechanical engineers and teachers here, we teach applied mechanics, and in applied mechanics we always start with cable. Because in cable the forces are easy to define. Forces are easy to control. So we thought of this cable because it was easy for us to control. But we somehow jump few steps, I guess. We were thinking of if two persons are here to operate this thing, we first thought of using a seesaw model, 2 people playing seesaw, and then this working by itself, just because of their weight. It will be, one will be this, but there will be a seesaw and other mechanism that will pull and push at the same time. We cannot do it like this. We can do this we cannot do. We have to pull both at the same time, push both at the same time. We thought of doing it using seesaw so that people don't have to use their hands. Instead, they can just use their weight and play seesaw and then get the shit out.
Still under refinement stage,
Yeah.
right?
Yes, it's complex to get it right, and it will take time. There'll be teething problems and challenges.
Once it's set up, I think there will be less, because we just have 2 systems here, 1 cable and 1 pump.
Did you think about having it the other way up? So at the moment the tyres upright.
No, the reason for us putting this like this is, as we discussed earlier, there will be sludge, right? So if there is sludge, we want our outlet at the most bottom part as possible. Because we want the gravity to do its job. We don't want it to jam there, the sludge to get jammed there. So if it comes from this pot, it will find its way very easily along here. You don't have to travel afar, and you don't have to take a vertical displacement and everything. That's why we decided to keep it erect vertical like this. Thank you.